Good afternoon. This is our 719 Mathematical Economics. We are studying discrete time dynamical systems. So let me share my screen. We're going to continue exactly from where we were. Let me open a new page. Okay. So there was this example of education and growth, and it was a slightly more difficult problem. Let me rewrite this. Maybe my notation could be different because I would have several, sketches of the same model. This is between 0 and 1. And in a moment, I will explain these variables and notation again. Okay, so these are greater than 0. All right, so this is again a discrete dynamical system. We have two variables here, the growth rate, G, and the, let's say, education investment or education spending in the economy. Medek has just joined. So we have parameters. So if you look at the first equation, the logic is this. So regardless of the education spending, or educational attainment, so it could be both, I mean, depending on your specific micro-funded model, this could mean a couple of things, but regardless of education, growth has a dynamic, all right? So you may imagine this using a difference equation. Since alpha is between 0 and 1, with no education, you have something like this, right? And with positive education and increasing levels of education, you have this, right? So if people are more educated, then for any level of GT plus 1 is larger, okay? So there's this type of dynamic between growth and education. And also, education spending responds to growth rate, at least if growth is larger than some benchmark, okay? So this cutoff value is, so if beta GT minus C is greater than 0, or if GT is greater than psi over beta, so you can define this as some threshold level, right? People start spending on innovation. People start getting more education. Why? Well, there could be, again, many different mechanisms, but one reason is skill depreciation. If productivity growth is faster, then people basically want to avoid their skills to depreciate, so they spend more time educating themselves with new technologies. Okay, again, so there are different types of mechanisms, but for one mechanism, you can check Odette Gallor's 2005 Handbook of Economic Growth chapter. Okay, so this is called Unified Growth Theory. So you can see, the full model that somehow generates a dynamic like this. All right. Now with this threshold, of course, this and with alpha here and this multiplicative term here, this is a nonlinear dynamical system, right? And one thing we ask, of course, where are the steady states? So is there a steady state? So if you look at this carefully, we will have two steady states. One steady state will have zero education, and the other will have positive education. All right. So now we can find these. So let me clear some space here. All right. So oops. So if E star is equal to 0, then I have G star equals theta times G star to the alpha, right? So G star is equal to theta to the 1 over 1 minus alpha, right? And now this is of course positive, given that theta is positive, but this must be what? This must be less than your threshold, right? Because you require education to be 0, so you say G star is less than or equal to G hat, all right? And G hat is defined again as psi beta, all right? So then there is this steady state with E equals 0 and G equal theta 1 over 1 minus alpha, okay? Now the other steady state, let me use this space. The other steady state, let me use a different color. So it will have E star greater than 0 and G star greater than 0. So obviously now G is greater than G hat, right? So we are looking at the growth rates larger than the threshold, so education will be positive, right? So then we have from the first equation G star theta lambda E star G star to the alpha, and then you have E star beta G star minus C, okay? So this is 2 equations in 2 unknowns. If you solve it, let me give you the result. If you solve it, okay, I didn't find the okay, so here's the idea. So here you have G star to the 1 minus alpha equals theta lambda E star. Now for E star, you replace this, okay? Now realize that this is a nonlinear equation, okay? If alpha is 1/2, you still have a chance to solve it because this becomes polynomial. But otherwise, there is no closed form solution, all right? So you can find G star numerically, okay? So that would be a function of alpha, theta, lambda, and psi, okay? But how do I know that there's a solution? Because if you think about it, one part is linear, so it is like this, okay? And the other part is basically like this, okay? So there could be actually more than one, even if G is positive, okay? There could be more than one. And that, of course, just a sec, that, of course, depends on the intercept here. So the intercept is theta lambda psi, and the slope, so I'm looking at the right-hand side of this equation, and the slope is lambda beta G star. So if this is positive, okay, you have the possibility of two steady states because this is just a parabola, right? This side. If you have this negative, all right, if this term is negative, then you have one steady state. Okay. So for the dynamics, you have something like this. So you want to look at the dynamics in two different cases again, right? Because if you have two steady states, you can only look at the local dynamics, right? Local stability, I mean. So this is a general rule. If you have, if this is the set of steady states, all right? So this is the set of steady states. For this example, you have EG pairs that are real such that ET plus 1 equals ET and GT plus 1 equals GT, okay? Now, if this set has only one element, if there's only one steady state, then you can talk about global stability, all right? So this is unique steady state, all right? Unique steady state. If you have multiple steady states, so the number of this set, so the elements of the number of this set is greater than or equal to 2, then you can only talk about local stability, all right? Now here we have at least two steady states. So I have G on this axis and E on this axis, right? So it will be like this. So one, you have, let me make sure, yes. So this was your, I will show you in a moment, but this is your EE locus, all right? And this is your so this is your GG locus, all right? So here, obviously, you have E equals 0, and this steady state you will find stable. And here, you will find, I will explain in a moment, you will find for this steady state, you will find a saddle-like system. Okay. Now let me explain how do I do that. So for the first steady state, we have, so this one right here. Our dynamics is this, right? Theta, GT, alpha. So what you want to do is to look at the derivative of the difference, GT plus 1 minus GT, right? So you want to understand how does this change when you have a change in, let's say, GT, okay? Well, we cannot actually, let me just look at my notes. So, I mean, just a sec. So here, forget about this because now I have only one variable, right? I have only one variable. So what I know is this. I know that it will be stable because this is my 45-degree line, GT plus 1 equals GT. And this is my theta GT alpha. All right, since alpha is between 0 and 1, this is a parabola. Since it is a parabola, the dynamics are non-oscillatory and stable. Okay, because the slope here, as we discussed last week, the slope here is, as you see, less than 1. Okay? For this reason, when E is 0, okay, when E is 0, then this steady state is stable, right? Because E doesn't change. And if G is larger, so this is, by the way, this is the threshold, of course. And this is theta 1 over 1 minus alpha, okay? Now, if you want to understand the behavior of this steady state, you should look at what? You should look at the difference between ET plus 1 minus ET, and how does this change, for instance, when GT changes, right? Now, ET plus 1 minus ET is equal to beta GT minus C minus ET, right? So, because this is ET plus 1 when G is larger than that. Okay? So this derivative is then equal to what? This derivative is equal to beta, right? So it is greater than 0. So if G is increasing, this must be increasing. So this is the sign of this. So then it must be 0, negative, and positive, right? So for E, I have minus, 0, and positive, right? So above the red curve, E is decreasing. Below the red curve, E is increasing. Okay. Then I want to look at the GG curve. So GG curve is like this now. So GT plus 1 is equal to theta lambda ET GT alpha. Okay. So I want to look at the derivative of this when, for instance, ET changes. Okay. And as you see, this is positive, right? So when E is increasing, again, this must be negative, 0, and positive. So we have negative and positive here. So above the blue curve, G must be increasing, and below the blue curve, G must be decreasing. So then we have this saddle-like dynamics, right? So on one direction, it is stabilizing, on the other direction, it's not. But of course, in general, we characterize saddle points as unstable. Don't forget that. All right. So in the optimal control theory, we had this particular reason why the consumer or the decision maker jumps on exactly the saddle path. Remember that? So remember the Ramsey model. So in the Ramsey model, we have K here and C here. So this is CC, this is KK. So there is a saddle path here, and consumer jumps exactly on the saddle path. Why? Because otherwise it either violates the feasibility constraint or violates the transversality constraint. Now, in a model like this, this can happen only by chance, right? Because I don't know the microeconomic dynamics behind this model. Okay, this is just given to me, and if the economy will converge to the positive steady state in a stable. So if this will be stable, this can only be happen by chance. If I'm out of equilibria, I will always move away. All right, I will always move away like this. Okay. So that's it. Now today, you will have a much formal understanding of all these. So these were just examples. And any questions about this particular example? So let me just stress one thing again. So when I give you a 2x2 model like this, okay, when I give you a 2x2 model like this, then you're gonna look for a steady state, obviously. Okay, you're gonna look for a steady state. So this is a set again that implies fx star y star equals y star, and so this is an and condition, and g of y star x star is equal to x star. Okay. Now after finding these steady states, then you can tell me the global dynamics by drawing a phase diagram. Okay, and in the phase diagrams, what you are looking for is the XX locus first. So the XX locus is like a set itself, right? So it's again XY pairs such that XT plus 1 equals XT, and YY locus is again pairs of X and Y such that YT plus 1 equals YT. Now to understand the dynamics in these regions, you're gonna look at how this difference change when XT changes, or how this difference changes when YT changes. All right. Similarly for X, you're gonna look at how this difference changes with YT, or you're gonna look at how this difference will change with XT. All right. Then you understand, for instance, the dynamics. Okay. So this is, of course, the global analysis. Okay. So today I will give you, I will basically focus on Galoh's discrete time dynamical systems. Discrete dynamical systems. So this is a textbook on discrete time models. So by using his notation, so this is in the syllabus, by the way, so you can check. This is in the syllabus. Using his notation, we're gonna work on the global and local analysis of systems like this. Okay, so this is entirely his notation. So XT is a vector in n-dimensional Euclidean space. So you have more than one variable, and phi is a function or a mapping defined in this way. Okay, So if you write it explicitly, you have x1t plus 1 equals phi1 x1t x2t dot xnt, all right? You have x2t plus 1 equals phi2 x1t x2t dot xnt, and this goes on like this. And finally, you have xnt plus 1 phi n x1t x2t dot xnt. Okay, so we want to understand the global and local properties of such systems. The steady state is defined simply in this way. So it is like an X star that satisfies this system in this way, right? So sometimes it is called a fixed point. Okay. And I think in the textbook, it is denoted in this way. Okay. So they're the same thing. This is the steady state. All right. And when I say a steady state, of course, I am talking about this, right? So be careful with the dimensions. Be careful with the dimensions. Okay. Now, the definition of global stability is this. The definition of global stability is this. Limit t goes to positive infinity if limit of xt is x star, okay, for any x0 in Rn. Okay, so if that's true, then this is global stability, right? For local stability, obviously, this must be true again. For all x, which is in the neighborhood of x star. Okay, so here, this is the epsilon neighborhood of x star, which is defined in this way. So it is a set. Okay, so it is a set defined in this way. So there are x's in this set, and these x's should satisfy this property. This is distance between x and x star should be less than or equal to epsilon. And epsilon here is some small positive number. So what is this distance? This is basically Euclidean distance. All right, let me give a brief definition. So here we have two vectors in the n-dimensional Euclidean space. So these are vectors. Okay, so the Euclidean distance is simply this. X1, Y1 square plus X2, Y2 square plus Xn, Yn square. So it is a distance, right? The vectoral distance. So in a 2x2 setting, you may also imagine this. Let's say we have two vectors and there is a steady state. Okay, so if this is xt, This is YT. Let's say this is X star, and this is Y star, okay? And suppose that this is X0 and this is Y0, okay? Now in the global stability, there is a path to the steady state, regardless of the initial point. Initial point could be here, 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 anywhere, okay? Because if you look at the definition of the global stability, it must be true for all X0 in Rn, okay? Now in the local stability, there is a ball here, okay? The radius is epsilon, okay? And X0 must be in here, okay? X0 should be in the ball, or so this is B epsilon X star, okay? And it doesn't have to be two-dimensional. It is true for any system in Euclidean space. All right, so you may imagine this as well. So let's say you have xt, you have yt, you have zt. So then let's say you have a steady state. So you have a steady state somewhere over here, okay? So then you may imagine a ball around this steady state, okay? Again, this radius is epsilon, okay? So this is the difference between local and global stability, more generally. Let me also emphasize that. So these types of local and global stability definitions also apply to continuous time systems, but your earlier textbook was not really specific about this, because at least you haven't seen the definition of a ball or the epsilon neighborhood of a steady state, but that's generally the idea, right? If you have one steady state, you can talk about its global stability or local stability. Again, if you have more than one steady state, you can only talk about local stability, because there could be many different steady states. And when you deviate from the steady state, you can be, you can enter the basin of attraction of the other steady state. Okay, so if you think about this carefully, so suppose that we are on R2, and let's say we have two steady states. So let's say one system is this, the other is, let's say, this, okay? So this is, let's say, XX locus, this is YY locus, so this is X, this is Y, so there's one steady state here, another steady state here. Now, you can only talk about the local stability. Why? Because stability is basically about deviating from the steady state, okay? So if you are here initially, and if you want to talk about the stability of the steady state A, then this deviation should not be too large, right? Because then if you deviate a lot, you can get, so imagine that all of these steady states are stable nodes, okay? Possibly there's a threshold there, okay? Possibly there's a constraint depending on X and Y, okay? There are models like this. So the dynamics of the system changes at that point, okay? Or I mean, we don't have to do it anyway, but so you can tell me that this is like this, all right? So then it looks like saddle, and here it is stable node. But if deviation is too large, then it is not possible to talk about global stability. Now we have less than a minute. It is 2:30 now. Let's meet at 2:45. All right, at 2:45.
Sorry, can you repeat this graphic after break?
Yeah, of course.
I couldn't understand the logic. Okay, thank you.
All right, okay, yeah. 2:45, we are meeting.